All right. Good evening, everybody. It's 5 o'clock on Thursday. Time for some more Calc 2. So we don't have a whole lot left as we talked on Tuesday. So I just want to give you a quick rundown, a reminder of everything. We're going to start differential equations today. You saw it in the online lesson. So basically, I'm going to go over the topics in that online lesson, give us an opportunity for some questions. We're going to do some of this stuff together. I've got a worksheet here we're going to work on. This was the worksheet in the invitation for today, but I'll put it in chat in case you haven't already downloaded it. So that way you have a copy. And basically what we're going to do today is we're going to go through all the topics that you saw in the online lesson. So what is a differential equation? You might look at a little bit at how you verify a solution to a differential equation, slope fields, and Euler's method that you saw to make sure we're comfortable with those. And depending on where we are time-wise after we go up to that, we'll do one of two things. We'll either break into groups and work on some problems from the worksheet, or I might actually go into what you're going to learn in the lesson on Tuesday, so that Tuesday we can focus on some other stuff and have a little bit of time for group work then. It'll depend on how everything goes, questions come up, we'll see. The other thing I want to remind you, I've updated the calendar so it's more reflective of what's going on in 2 weeks. So we have class today. We'll finish up, we'll do more differential equations on Tuesday. Might be some spillover into Thursday of next week. And I'll also take some time Thursday of next week to talk about the final exam. You have access to the review materials and course content. Then the following week, we do not have any scheduled class meetings because I want to give you that time off. I know you've got other final exams, you've got take-home problems from me, you got a final from me. So we won't have any class meetings per se. But I mean, I'll still be available via email. You'll still have access to tutoring and everything. But I did put on the calendar that Tuesday I will be proctoring exams on SEC campus, if you want to do that. Thursday, I'll be proctoring over Zoom like we did for the midterm. And then you could actually also use ProctorU to take the final exam anytime that week that works with your schedule. My advice always schedule that as early as possible because that's when you're going to get the most options on times, right? If you have any questions about scheduling the midterm or, the options to take it, shoot me an email, let me know. But I just want to give you the opportunity to get that taken care of and out of the way so you don't have to worry about that. And the take-home problems will be due by 5 p.m. of that Thursday, which is December 16th. Which is when we're going to do proctoring over Zoom. So still have 2 more weeks for the take-home problems. We've got the first one. The next one, let me see, I don't know if we're going to get far enough today. Let me see, what do I got here? Oh yeah, actually, the second take-home problems, because I want you to have the time. The second take-home problem will be available tonight after class, because we'll cover it enough for you to at least get started. Okay. All right, so just want to take care of those logistics. I'll remind you at the end of class, and as always, you can always email me about that stuff. All right, let's jump into differential equations. And again, if you're able to have the worksheet. It's about 13 pages. There's a lot of problems on here. We're not going to try and get through all of them, but what I want you to do is you're going to follow along. You can, if you want to print this out, or if you use a tablet and you want to write solutions in here, totally fine. Guys, if you can do the problems on this worksheet, you'll have no problem with differential equation on the final exam. I think the only thing, let me just double check. Yeah, the only thing that's not explicitly covered in this worksheet is verifying the solution to a differential equation. And like I said, if we don't talk about that today, we'll look at that either Tuesday or Thursday of next week, and it's in the online lesson and the review materials. It's not difficult, but if you haven't seen it before, you wouldn't know what that means. All right, let's jump into this. So what we're going to do, we're going to be kind of like one big group today. Right now there's 4 of us. And we're going to just start working through this worksheet. And some of the questions I'm just going to let you guys think about and answer. Especially for this first page. And then we'll keep track of the answers. I'll keep track of what we decide on here. But I want you to have the solutions for yourself, because I want this stuff to make sense to you. So the first thing that we want to understand is, what is a differential equation? A differential equation is any equation that involves the rate of a function. So because you guys have been dealing with derivatives through Calc 1 and 2, when you're doing that, you're actually dealing with a lot of differential equations. And it turns out you guys have solved some differential equations. When you do the antiderivative of a function, that actually could be considered solving a differential equation, because you had an equation that had information about the rate of a function, and you use that to find the solution. And as you can see in this first sentence here, solution to a differential equation is a function. Okay, so let's talk about what that means. So first off, like I said, some of these questions I'll throw to you. If it's newer stuff, I'll do it on my own. But what about number 1 here? How many solutions can you find for y prime equals 0? And now, before you answer, that would be a differential equation. Let's think about what that means. Y prime equals 0. Well, how many functions can you think of that have a derivative of 0? And you can respond in chat, or if you want to turn on your mics, whatever's easier for you. How many functions? Yeah, go ahead, Mark.
Infinitely. Infinite, because if it's like, yeah, all constants.
Nice job. You guys all 3 got it. There's infinitely many, right? Because because the solution to this would be y equals c, where c is a constant. So any constant has the derivative of 0. All right. What about something like y prime equals 1? How many solutions do you think that has? So yeah, same thing, right? Now, for this, what does this mean? This means we have a slope of 1. So now we would say, okay, well then y equals x plus c, where c is again a constant. Like I said, guys, when you were doing antiderivatives back in Calc 1, you were technically solving differential equations. And now we have y prime equals y. Now this is going to be a little bit less familiar to us, right? We're used to like y prime equals x, or something in terms of x. But when y prime equals y, this is more typical of what you would see in differential equations, is some equation that relates the rate, y prime, with the amount. Now, how many solutions do you think there are to the equation y prime equals y? Same thing, right? Yeah. Yeah, y equals 0 would be 1. There's actually, this one will be infinite as well. Y prime equals y. So all 3 of these cases, we have infinitely many solutions. 3, if we wanted examples for solutions to y prime equals 1, well, we have the general solution here. So really anything, y equals x plus 1, y equals x plus 2, y equals x plus pi, right? If you want to get a little creative. Any function any linear function with a slope of 1 has satisfies the equation y prime equals 1. Okay. The thing that what this creates is a series of parallel lines because what they have in common is their derivative or their slope. Now this one this one is really interesting. And before we end today, I'm going to show you how to analytically solve this differential equation y prime equals y. But let's talk about this differential equation without actually knowing how to solve it. Let's think about what this means. This means we're looking for a function that is its own derivative. And now y equals 0 is actually an example of that. But what's another example? What is a function that is its own derivative? Very nice. So, and that is that you actually gave a general solution there, Knight, which is great. So one example, our most basic example would be y equals e to the x. But it turns out any constant times e to the x is its own derivative. Now, if it was additive, it wouldn't be true. And so we get the general solution, y equals c e to the x. Like I said, we're going to come back to this one and we'll look at how to solve it analytically later. But I just wanted to reason through it with what's actually being asked. So the further you guys go into differential equations, which we'll scratch the surface of them between today and Tuesday and Thursday. But for those of you guys who go on to take a differential equations course, you're going to see e to the x a lot because it is the solution of what we call a first order differential equation. First order because it only involves the first derivative, where the first derivative is directly related to the amount of the function. So we see e to the x a lot in differential equations. As I go through the packet, as always, guys, feel free to ask questions. I got chat open, so if you want to ask in chat, if you want to turn your mic, let me know if you have if you want any clarifying questions. Because you saw this stuff in the online lesson, but you just saw it for the first time. So this is as we go on, this stuff might be a little more straightforward, but as we go on with this is going to be a really good opportunity for you to ask questions about slope fields, the Euler's method, that kind of thing. So don't hesitate to ask questions. All right, let's move on to the next page. So now we're on to the second page. And now we're going to talk about finding a unique solution. Again, this is something you guys have done before. What happens here is we have a differential equation plus what's called an initial condition. All right, so these are in differential equations get called initial value problems. So what you would do with something like this is, okay, we've got the differential equation y prime equals 1. Well, we know from what we talked about on the last slide. Sorry, that came out very nice. Y prime equals 1. And what we know from the last slide is that gives a general solution of y equals x plus c. This is what we call a general solution because what this is what's we call a family of functions, because for every value of c, we get a different function, but they all share the same slope. Now, to find the unique solution, we need what's called an initial value problem. Well, we're told that this thing has to go through the point 5, 7. And this is just like solving for c back when you did antiderivatives. You plug in 5 for x, 7 for y. You can see that c has to equal 2. So the unique solution is y equals x plus 2 to this initial value problem. All right. So a lot of problems we're going to do, especially once we get into the applications, are going to be what are called initial value problems, meaning that we're given some kind of initial condition so we can get the unique solution. And here's something that's going to take a little bit of getting used to. This is the unique solution to this differential equation. So the solution is a function. We're used to solving equations where the solution comes out to be a number, or maybe it's a couple different numbers. When we're solving differential equations, the solution is actually a function. So when you're finding the antiderivative, that's finding the solution to a differential equation. All right. Now in 2, we've got a differential equation of y prime equals x to the y. And now we're told that the solution is ae to the x squared over 2. Well, this is a perfect opportunity for us to see how to verify the solution of a differential equation. Let me clean something up here. I forgot to put in the y equals, and I want that in here just so you can see what this looks like. Because like I said, I want to make sure we cover everything that's in the online lesson because stuff is new. So the solution to that differential equation, the general solution is this. So you know what, before we find this, the unique solution, let's verify that this is the solution to this differential equation. What we do is we're going to do it via substitution. So we know y. Well, we can also find y prime, which is just the derivative of y, which is ae to the x squared over 2 times the derivative of the exponent, which would be 2x over 2. Cancel those. And maybe we clean this up a little bit. A times x e to the x squared over 2. That is our y prime. Now, what we do in order to get this to work out, or to verify, I should say, not to work out, but to verify, we do substitution. So what I'm going to do is I'm going to take what I found for y prime and sub that in for y prime, and what we were given for y and sub that in for y, and just make sure that I have a true statement. So y prime is a x e to the x squared over 2. And then over here, well, we have x, and then we substitute in the y, which is a e to the x squared over 2. And we can see that these are in fact equal. And what we've done is verified the solution. Okay, so that's what, when you hear that term, verifying the solution to a differential equation via substitution, that's what you're doing. If it's a first order, you take the first derivative and you plug in the function in the first derivative. If it's a second order, meaning it involves the second derivative, you find the first, second derivative, you plug all those in, and you see what comes out. Okay, so that's verifying the solution. And then if we wanted to involve the initial condition, well, we got the initial condition, 0, 3, it's initial condition. That means when x is 0, y is 3. So we know that our solution is y equals ae to the x squared over 2. We're going to plug in our initial condition and solve. 3 equals ae to the 0 squared over 2. 0 squared is 0, divided by 2 is 0, e to the 0 is 1. This gives us a equals 3. And so our unique solution to this initial value problem is 3e to the x squared over 2. Questions about that one, or questions so far? Yeah, I know we haven't really gotten into a lot of the stuff that's in the online lesson yet. We're going to. Okay. So, give me just 1 second. Yeah, okay. All right. Moving on. So, what we're doing here is we're starting off basic with stuff we're already familiar with. We're familiar with antiderivatives, and we're building our knowledge from there. All right. So, next thing that we're going to talk about is slope fields. Okay. So, what I want to do is I first want to start to draw one. And I'm never going to have you guys draw a slope field. You're going to see how messy mine come out. But let's say that we have the slope field, y prime equals y. We'll start with a very basic one, the one that we were just looking at. We're going to use this guy a lot today because it's a basic one for us to find the function. We already know the general solution. So what a slope field is, and you can see images of slope fields. You saw them in the lesson. It's a bunch of little lines because what's happening is we're representing the slope based off of our derivative at each individual point. So let me give you an idea of what that looks like. And just as a reminder, we know that the general solution to this is y equals c e to the x, or a e. Some people use a, c. It doesn't matter as long as we know it's a constant. That'll be something of interest when we actually look at this slope field. All right. So I'm going to do my best to show you how we do a slope field here. It's a little, I'm not the best at drawing with this, as you guys have noticed over the course of the semester, but I will do what I can. Okay, so this is, the only reason I like doing this is if you create a slope field, you get a better feel for how it works. So what we're interested in is the differential equation y prime equals y. All right, so we're focusing on this. Oops. We're not worried about the general solution right now. This will come, we'll talk about this later. So this tells us what our slope field is going to look like, and this is how it works. What you do is you go around to points in the plane, and based on what the point is, you plug those into your differential equation to get the slope, and then you draw a line to represent that slope. For example, if we're at the origin, right here, we know y is 0 at the origin, which means our derivative is 0, which would be a horizontal line. So we would represent that with a little horizontal line like that. Okay? Well, this is going to happen anytime y is 0 because this differential equation only depends on y. Oops. So what we end up with is a bunch of lines with a slope of y, excuse me, a slope of 0. Sorry, guys. Along on the x-axis. Okay, well, that's good. Not the most interesting thing, but let's see how this plays out as we go to other places. Well, what if we come up here to the point 0, 1? Well, now the y value is 1. So what we would do at 0, 1 is draw a little line representing a slope of 1. So literally what you do to create a slope field is you go to points in the plane and you plug in that point into your differential equation to get what the derivative is. And then we use these little lines because remember, the derivative is an instantaneous rate of change. And so, it actually probably isn't, this is probably longer than it has a slope of 1, but at least it gives us an idea of direction. Now, any place y is 1, we're going to have a slope of 1. So on this horizontal, I wish these lines were coming out a little more parallel. Let's see if I can do a little better. We got a bunch of lines with a slope of 1 along that horizontal. And that's kind of how we build a slope field. If we go up again to where y is 2, we get something that's a little steeper. And what this does is it gives us a general idea of the flow of our differential equations. Now, just like we have the C, where we have a general solution, not a little bigger. Ideally, these lines would all be sized. I'm having a little bit of a tough time getting them to come out the same size. If we go up to 3, it gets even steeper. So the slope at each point is basically based on the point itself. What are the xy values? Because that's what the differential equation gives us. It gives us the rate of change at any point. If we go to -1, we get a negative slope. So we're basically going to see a mirror image of what we just drew. All right. And again, I'm not going to have you guys draw one of these, but knowing how they're created, I'm just going to do one more. Knowing how they're created helps us understand how they relate to the differential equation. I'm not doing the best job on this one, but
So
yeah.
Wouldn't the slope be going up at 0 though? Since like e to 0 is 1.
Well, remember, this part, the y is the solution to the differential equation, y equals c to the x. So we don't want to get those two conflated. Maybe I shouldn't have written this on here just yet. That is the solution. And we'll see how that's involved
I
here
see
in
what
just a
you
second.
mean.
But this is what gives us the information about the rate of change. And that's probably my fault for drawing that up, put the solution on too soon. But we're going to see very quickly. Thanks, John Paul. We're going to see very quickly how the solution relates to the slope field. Other questions about how I drew this very messy slope field? So here's a better image of it. This is the slope field. So I'm already giving you this one. So this figure 2 is going to match up with the differential equation E. This is what this slope field looks like when it's generated by a computer. Okay. Now let's talk about the solution, because this is actually, you know what? Let's not talk about the solution yet. Here's what I want you guys to do. We already know that figure 2 goes to E. What I want you guys to do is to see if you can see if you can match the other 5. Okay, so just take a few minutes. This is a matching problem. Like I said, I'm not going to have you generate slope fields. Matching slope fields is what I would give you on, say, the final exam. So this would be like a final exam type of question. So why don't you guys take a few minutes and match up the other 5 slope fields and basically use that same thinking. Okay, look at where the slopes are 0. Which differential equation makes the most sense? Look at where the slopes are vertical. Which differential equation makes the most sense? Let me ask you guys this. Do you guys want to do this on your own, or do you want me to put you in a breakout room so you guys can discuss these? What do you think? Okay. So why don't you guys just take a few minutes and match, and then we'll go through them. You guys we'll build an answer key. I don't know. Let's take maybe 5 to 10 minutes. Once you feel like you've got them all matched, let me know, and then we'll go through and see how we did. Okay. So just take a few minutes. I'm gonna I'll show you my mics. Okay, so guys, thanks for posting in chat and keeping me updated. I'm gonna zoom out so we can fit everything on here. Okay, so let's go through this. Let's first off, let's mark the one we already know, right? We already know that this one here. Oops, how did that happen? We already know that this one here is right. Okay, so let's talk about figure one. Which differential equation do you think creates this slope field? I like it. And you know, this one I think makes a lot of sense, right? Y prime equals 1. That's telling us our derivative is a constant, and we see it reflected in the slope. Every single thing on there has a slope of 1. Okay. What about figure 3? This is a little bit tougher one. What did you guys think on this one? I like it, guys. F. Perfect. Because notice what happens. Along the line y equals x, which would be that 45-degree line, we have all horizontal lines, which means we have a slope of 0 when y equals x. Well, if we look at this differential equation, when x and y are the same, we're going to get a slope of 0. And also, when x is larger, we're going to have a positive slope. When y is larger, we're going to have a negative slope. So that's why we see down over here and up over here. It creates that really interesting shape. We get some pretty cool images with these. Let's see. We've got F, we got E, and we got C. 3 left with 3 graphs. What about figure 4? Again, a little bit trickier one. D. So we're thinking D for, let's see. Okay, so this is a tough one. All right, so here's the problem with it being D. Okay. Here's what I like about D for figure 2 or figure 4, sorry. When x is 0, we should get horizontal slopes. Okay, so along the y-axis we get horizontal slopes. But notice that y is in the denominator here. When y is 0, we should get undefined slopes. So we should get vertical lines along, and that's when we're on the x-axis. But it looks like it's horizontal along the x-axis. So which slope field looks like it has vertical lines along the x-axis? Yep, exactly. So that, good. So this one's actually going to be B. And again, guys, this is tricky, and this is the first time you're doing this. Okay, so it's perfectly natural to get some of them wrong, and I'm just telling you the stuff that I look at. And what I notice is that along both the x and y axis, I have horizontal slopes. So that tells me if I'm on the x-axis, that means y is 0. So when y is 0, the slope should be 0. When x is 0, the slope should be 0. And the only one that does that is this one, because B, because of the multiplicative structure. So what does that leave for figure 3? Very nice. And by process of elimination, and you guys probably would have gotten this one anyways, right? This one has to be A. And we can kind of see the sinusoidal curve in the slope field. Nice job, guys. It is kind of obvious, right? And that's okay. I mean, it's still one of our differential equations. I think these three, this one, and this one, are a little bit more difficult because, again, they're not so obvious. But like I said, you're not going to be drawing any slope fields. What we just did is more like what you would see on a final. You'll get more practice with slope fields in the homework. So I don't want you'll get some practice and some time to work on them. And again, the biggest thing is to look at particular points and see which ones make sense with the differential equation. So the things I look at are, where is it horizontal, vertical, where is it positive, where is it negative? Okay. Any questions about this matching question? All right. Again, my goal for today, guys, is just to get you feeling more comfortable with the stuff you saw in the online lesson. So you let me know how it's going. All right. Now, we talked about initial value problems before, and that's how we find the C. Well, when we don't know the C, what we get is a slope. But once we turn this into an initial value problem, then, sorry, I got enough of that. Then we can actually get the unique curve. Okay, so let's turn this into an initial value problem. Let's say it has an initial value. Let's make it something fairly simple. How about 0, 1? Okay. Well, if we plug that in, we know that C is going to equal 1. And we get the function y equals dx. Okay, great. That we already know how to do. That's basically solving for the constant in our general solution. Here's how this lines up with a slope field. If we have an initial value of 0, 1, what we do is we go to our slope field and we mark that point on our curve. And then we use the slope field to draw the line that goes along with it. So I'm basically just kind of mimicking my slope field. It's not going to be perfect. But what I have here in purple is the graph of y equals e to the x. Okay? So the unique solution of a differential equation is a function, and that means we can also represent it graphically. So what I have in purple is the unique solution. What's in red is the general solution to the differential equation. So a slope field is a graphical representation of the general solution. The graph is the graphical representation of the unique solution. Questions about that? Guys, the internet is literally filled with a bunch of different slope field calculators. Because one of the things you're going to have to do for your take-home problem is graph the slope field. So you're going to have to use one at some point. Don't care which one you use. You go with personal preference. Because we've used Desmos before in here, let's use Desmos now. All right. So if you want to get here, you can basically Google a slope field plotter, and this is going to be one of your solutions. We might look at another one too, just for fun, just to see how they're different and how they're the same. But let's start with Desmos. Okay, so right here is where I define my slope field. G of xy equals y. So that was this, what they're calling G of xy, we're calling y prime. So that, you can see how we have basically that same slope field. Now they do have this movable point, which will put us, which basically will give us the slope at any point in the slope field. And if we wanted to add the unique solution, if you wanted to add the unique solution, well, we found it. It's y equals e to the x, so we can just add it to our curve. And there's our unique solution. It goes through 0, 1. And that gives us our curve. If we did another one, let's say we had, I don't know, let's do more negative one. Let's say we had a initial value problem where it has to go through, actually it doesn't even, we'll leave it at 0 for now. It doesn't have to be at 0. X could be anything. How about 0, -3? Well, in this case, that would make a c of -3, so y equals -3 e to the x. What that -3 does, we know this from algebra, that reflects it over the x-axis. So these are two unique solutions for our two initial conditions. And that's how the solution relates to the differential equation graphically. It is the graph that goes through our differential equation. Questions about that? All right. Just for kicks, here's another slope field calculator. This is one that I found online. Again, there's so many of them. And for our purposes, we're just going to be using one ODE. ODE stands for ordinary differential equation. That's all we're going to touch on today. We're not going to do polar. We're not going to do systems. For those of you guys go on to differential equations, that's what you'll see. Right here is where you put in your differential equation that gives the slope field over here. You can change the dimensions here, and you can change the number of line segments, okay? Now, if you want to put in the curve that goes with it, we're going to be learning Euler's method here shortly. But now, guys, remember, this is a different differential equation than the one we just did. This is x plus y. That's actually not going to be a differential equation we're solving this semester by, analytically, but Euler's method, absolutely. So you get an initial condition, you can put it in here. We'll talk about what h equals 0.1 means in a second, and then submit. And look, there's our solution. It goes to the point 0.1 right here. If we change the initial condition to I want it to be something that'll be on here. 2, 1 will work. Notice now it has to go through 2, 1, and then again it follows our slope field. So there are others out on the web. So like I said, you can just do a search for slope field plotter and play around with them and see which one you like best. If you like Desmos, Desmos works. If you like this one will work. Both of these will work for the take-home problem, for the homework. So and a lot of the other ones will too. All right. Questions at this point? Okay. Now, one of the other things is we're looking at the slope field is we're looking at slope fields. Another thing that we look at is how these slope fields behave. You know, actually, I'm going to hold off on that. I'm going to save that for next class meeting. We'll talk about stability and equilibrium solutions. So we'll save that for Tuesday because it's more interesting in applications than it is on some of these general differential equations. So I was thinking about doing it now, but let's talk about Euler's method. Okay. You saw this in the online lesson. It probably was a little weird. Euler's method is a numerical method for calculating a slope. Okay. So we're gonna do one together because we started with dy y prime equals y. Let's take a look at this, and I want to talk to you a little bit about how this table works. All right. So we are going to, let's see. Yeah, let's do this one here. No, actually, we'll do the first one. Okay. So here's how Euler's method works. Euler's method is a numerical solution to a differential equation. When is that going to be needed? Well, when you can't find the solution analytically. Now, the reason I'm specifically choosing this one is because we can find the solution analytically, so we can check our answer. But I want you to see what Euler's method does and how it works. So Euler's method actually kind of circumvents finding the function that is the solution to the differential equation, but we'll still find the value of the function, or estimate, I should say, not find, estimate the value of the function at a given point. And that'll make more sense as we go through an example here. So we're going to do this one for y. It's too big. Yep, got to come down one. And so this is how this works. And this is, guys, this is how I recommend you make your table, because this makes it very easy. All right, so to do Euler's method, you need a couple things. You need a differential equation. So we have that. So this is going to be our Euler's method example. And we are doing y prime equals y, or dy dx equals y, however you want to do it. Okay. So what we're doing is we're starting at 0, 1. And then we actually want to see what is the value of the solution to this differential equation at 1. So a question for this would be, say, use Euler's method to estimate y of 1 using 5 steps. Okay. Now, this notation is a little bit new to us, but it's a combination of two notations. We're used to that function notation where we say f of 1 is f with 1 input. Y of 1 means y would be the solution to this differential equation. In other words, we know the solution. We know the solution is y equals e to the x. So y of 1 would equal e to the 1. Would equal e to the 1. Okay, so that's what this notation means. It's not confused. It's not hard or anything. It's just if you haven't seen it before, it looks awkward because up until now it's always been f of x equals or y equals. Now it's kind of like we're saying y of x equals. So that's basically what we're being asked to do. Is we know that y of 1 is e, but what we're going to assume that, hey, maybe we got a differential equation we can't solve. So what Euler's method does is it estimates y of 1. We're going to do 5 steps. And so what we do is we first calculated delta x. Well, so we look at how far we're going in x. We're going from 0 to 1. So we do 1 minus 0, starting x, ending x, over the number of steps, equals 1/5, or 0.2. That is our delta x. Okay, so that is going to be our change in x for this problem. So we can, and we'll do it here in a second, we can fill in the x column now. We know the x values. What Euler's method does is it uses the slope at each individual point to steer us in the correct direction by multiplying it by delta x. So we're going to go to 0, 1. We're going to calculate the slope with our differential equation, multiply that by our change in x to estimate our change in y, which will give us our next point. Then we'll go to the next point and calculate the slope, put that in, and then it's just an iterative process, meaning we repeat that over and over. All right. Now remember where your slope comes from. It comes from your differential equation. Okay. So let's see what this looks like. And guys, feel free to ask questions because there is usually a Euler's method problem on the exam. We'll use the calculator. I'm just going to write on this worksheet. All right. So again, right now I'm at the point 0, 1. So if we're using our, I know it's kind of cut off here. Remember this is our slope field. That is what's giving us this slope. So our change in y is equal to our slope at 0, 1. Well, the slope is going to be 1, right? Because y is 1, 1 in here, you get 1, times our change in x. So times 0.2. That got a little messy, apologies. Times 0.2. That is our change in y, 0.2. So we take y plus our change in y. Didn't quite make these boxes big enough. I take y, I add on the new y, and I get 1.2. Now, like I said, we can fill in the x column right away. Delta x is 0.2, so it's going to go 0, 0.2, 0.4, 0.6, 0.8, and then finally 1. Well, remember, we wanted to estimate y of 1. So we're looking to get our solution, which is going to be when we fill in this box right here. Okay? Now, again, this is just an iterative process, meaning I do the same thing over and over again. It's just my slope is different because I'm at a different point. So when I go to calculate my delta y this time, well, now my slope, basically you take this whole point, because some of these differential equations will be in terms of x and y. You take this point, you plug it in. So our slope here is 1.2. And that gets multiplied by 0.2. So, 1.2 times 0.2. So that's my new delta y. And again, that gets added to the most recent y value. So 0.2, 1.2, add the 0.24, you get 1.44. I want to pause there to see if there's any questions so far. Probably what we'll do today is I'm going to probably find a way to give you guys some time to do one Euler's method problem. Put you guys in a group and try one, just so you get a little bit of, just so you get some practice with it while we're together. You won't have to. John Paul asked if the boxes will be bigger on the test. Remember, the test is going to be like the midterm. It'll be multiple choice, so you can make. You guys will create this table, so you can make the boxes as big as you want. Because you're right, I made them too small. All that you're going to need for the test is to find the correct answer. So you could use a blank sheet of scratch paper and make it as big as you want. Take up all the room you need. The tables on the worksheet are just more of a guide. Don't feel like you have to, because a lot of these decimals get a little long. So you don't feel like you have to fit all this stuff. Okay, next delta y. So now our slope is y, but now it's 1.44 times our delta x. So 1.44 times 0.2. There's our new delta y. And I'll record that in just a second, but that gets added to our old y, which is 1.44. And this is going to be something you're going to want to have your calculator for. These can be done by hand, absolutely. Euler's method was invented before there were ever calculators. But for the exam, you're going to want to have a calculator for this. And guys, I'm not going to ask you for any more than like 4 or 5 steps on the exam. It's just to make sure you understand how Euler's works. You don't need to go through 10 or 20 steps on an exam. 1.728. So here's what's happening. We're basically moving by 0.2, which is going to be kind of hard to draw in here. So we started at 0, 1. And basically, we're just kind of numerically moving along the slope field until we get out to what we would get at 1. So we're going to basically get to about right there. That's a little low. Actually, we're going to be up a little higher. No, I promise not to make it go to 100. But what I would tell you is, remember, if I did make you go to 100 on the take-home problems, remember, you can use technology. So there are plenty. You guys can find online Euler's method calculators because it's very easy to code. So feel free to use one of those online Euler's method calculators to check your answers, by all means. I'm not going to have you do that on the take-home, but you will do one of these on the in-class. It'll be like 4 steps. So basically, as long as you know how to set up this table and how it works, I think you'll find Euler's method pretty straightforward. All right, next one. We take the y, 1.728 times the 0.2. You're going to see the numbers start getting, as far as the number of decimals, they start getting pretty long. But check this out. I can do it all in my calculator. There's my slope times 0.2. There's my change in y. I add that to the old y. 2.8. And now I am at 2.0736. And I'm not going to write out the next one. I'm basically doing the same thing. That's the nice thing about Euler's method. Once you have it down, it's easy because literally you're just doing the same thing over and over. Slope times 0.2. Add that to our old one, 2.0736. And our estimate of y of 1 comes out to be about 2.48832. So what we find with Euler's method is that y of 0, y of 1 is approximately 2.48832. Okay, we know the actual answer. We know y of 1 is e because we know what the solution was, and that we know that e, and don't feel like you have to memorize. There's no reason you're gonna have to memorize e or anything, but if you don't know it, you can always put it in the calculator, e there. E is about 2.718282. Let's just stop there. So clearly our estimate was lower. All right. Let's talk about that for just a second. A lot of times, if we look at the slope field, we know if we have an overestimate or underestimate coming from Euler's method without actually knowing the actual answer. And that's because Euler's method is made up of basically tangent lines. That's really all it's doing. So basically what we were doing on as we went along here, is we were doing tangent lines. So tangent line, tangent line, tangent line. Well, think about this. If the curve is concave up, if our solution is concave up, then tangent lines are always going to sit underneath the curve. Let me drop that to slope field, maybe you can see it a little better. If that's our slope field, tangent lines are always going to sit underneath the curve because it's concave up. So it makes perfect sense that we have an underestimate. If it were concave down, it'd be the exact opposite. We would expect an overestimate. If the concavity changes between our starting point and our ending point, we lose the guarantee of an overestimate or underestimate. Now, there are ways of still getting that based on the amount of concavity, but that's not going to be something we're going to be worried about. But when you know that you look at your slope field and you say, oh, it's concave up between 0 and 1, right there, we already know that whatever Euler's method gives us is going to be an underestimate of the actual value. Same thing like if we did one below, if we were starting underneath because it's concave down, our tangent lines would all sit on top. So anything we get from Euler's method would be an overestimate. Questions at this. So just to get a kind of a gauge, how are you feeling about Euler's method? Like if I were to say, hey, do an Euler's method problem right now, how do you think you feel about that? And you can put it in chat or turn your mic. I just kind of want to get an idea, because I know basically you saw it in the online. Well, you've seen my drawing, so if you don't even worry about the drawing. Okay, so yeah, we picked an easy one. Let's pick one. Let's see if there's one. Let's look at one that maybe has a different differential equation and talk about it. That's kind of boring. And oh, the drawing isn't important, John Paul. The drawing is not important at all. The only reason, well, I shouldn't say it's not important at all. It gives us an idea of what's going on, right? We want to kind of match up what's going on graphically with what's going on numerically. That said, though, you guys aren't going to have to draw these graphs because we got technology to do it for us. All right, what do we got for differential equation here? So, Naif, to your point, don't let the differential equation bother you. Here's what I mean by this. Let's look at this one. We're going to go from 0 to 2 in 5 steps. I know you can't see it anymore. Actually, you know what? Let's do. I'm going to make up a differential equation. So this one, we're getting away from the sheet. Let's say y prime equals. Let's do one that has both x and y. Let's just say this is our differential. Actually, yeah, let's do that. Let's make it even a little bit more interesting. Let's make it x squared over y. Here's the thing. The only thing the differential equation is used for is finding the slope. So we'll do 5 steps to go from 1 to go from 0 to 2. So our delta x is 2 minus 0 over 5, or 2/5, or 0.4. So right off the bat, we can fill in this column. 0.4, 4, 0.8, 1.2, 1. I'm only going to do a couple on this one. Actually, maybe we'll do. Well, the reason it's 2 minus 0, well, we need to end at 2, and we're starting at 0. So that's where the 2 minus 0 comes from, and then we had 5 steps. So it's very similar to when you were doing numerical integration, right? You had the interval, and then you divide it by the number of rectangles. We're doing the same thing. We're doing the interval from 0 to 2 in 5 steps, 2 minus 0 over 5. So our delta x is 0. Okay, so then our y starts at 1, and we got to calculate our delta 1. Well, we take these numbers. So 0 squared over 1, that's our slope. All I did was take these two numbers, plug it into here, and then that gets multiplied by our delta x. Now this is kind of a boring one. This came out to be 0, and 1 plus 0 is 1. So let's do a few more steps, and hopefully Hopefully I can fit these in without making, I'm going to write this one over here. It's just going to get too messy. I wrote the first one a little big. Okay, so now we're at this point, 0.41. So 0.4 squared over 1 times 0.4. So in this case, we actually just end up with 0.4 cubed. And that gets added to our old value. And so that means this is going to be 1.064. Because we take the 1, this came out to be 0.064. 1 plus 0.64 is 1.64. So I want to make sure you guys see where all the numbers are coming from, because guys, I guarantee once you get Euler's method, you are going to say, wow, this is easy. It's just a lot of computations. But it's new, and I want to make sure you guys are comfortable. So if we do this one, our differential equation, x squared over y, so 0.8 squared over y, which is 1.064. So you can see the numbers are getting a little messier, not just because of how I write it. That's a 0.8 times our delta x, which is 0.4. Apologize that I don't have more room on this. Probably should have zoomed in more. But now we would do, okay, we do exactly what it says. We do 0.8 squared divided by 1.064 and then times 0.4. There's our delta y for this one. And then that gets added to our previous y, 1.064. Oops, wrong answer. And that makes this next one 1.30460. And the more stuff you can keep in the calculator, the more you're going to avoid round off. So I can't emphasize that enough. Keep as many decimals as you can. You know, you can see that I'm doing almost all of this in the calculator. So when I go to do this one, let me show you how I might do this one. Okay, so delta y is going to be x squared. X is easy, it's just the 1.2 squared over the old y. Well, I rounded that up. So in the calculator, I'm going to use answer so that I don't have to worry about rounding, right? What do I mean by that? So check this out. If you're not familiar with this, I'm going to do, I got the 1.2 squared divided by second answer, because that's going to just take that whole unrounded number for me, times 0.4. There's my new delta y. That's going to get added to 1 point. And I probably could have just put the plus answer here and had it done all for me. I'll show you what I mean in the next step. 304601504. So there's this y. Now, obviously, I'm not, writing wise, I won't be able to fit them all in, but when you're not confined to trying to write in boxes that are just too small, you can make the numbers as big as you want. 6115636. And now here's what I'm going to do. I'm going to do this last one all at once. All right, so I know that delta y for this one is going to be 1.6 squared. I don't know why I wrote 1.4 here. It should be 1.6 over answer. Man, did I run? Guys, this is terrible space management. I apologize. All right, so I'm going to do it all in the calculator, and so I don't have to rewrite anything. I got the 1.6 squared. That's the x squared. Then divided by my previous y. times my delta x, and then that gets added to the previous y to get my new y. And there is our estimate. When all is said and done, we get that y of 2 is approximately 2.332560187. Questions about this one? Did this help to see where the numbers are coming from? I know I apologize about how messy it is. But how we do the steps, and I want it to feel it should feel very mechanical. All you're doing is using your differential equation, calculate your slope, multiply it by your delta x, add it to your old y. Calculate your delta y, add it to your old y. Calculate delta y, add it to the old y. That's all we're really doing. It's just to calculate the delta y, it's the slope times the delta x. So what I'll recommend you guys doing when you guys are practicing Euler's method, make a table that looks like this. Obviously give yourself more room, but if you write the top row like this, you fill in the number of steps, you do your x first. This helps you organize Euler's method, because that's all it is about, is organization. Questions at this point? All right, I want to leave this up here because we're going to come back to this actually after we do this next part. All right, so here's what we're going to do. We only got about 15 minutes left. Not enough time to break into groups and do an Euler's method. So, sometime between now and Tuesday, try an Euler's method problem. We can always review Euler's method on Tuesday or Thursday next week. So sometime between now and next week, try an Euler's method. It could be one from the worksheet, it could be one from the homework. See how it goes. And that way you have time if you have questions. All right. Now, let's talk. We're going to not skip ahead, but we're going to move ahead into what is going to be one of the first things you're going to do in the next online lesson, because I want you to already be familiar with this part so that on Tuesday we can focus on applications. And I told you before, we know the answer of this one is e to the x, because we have an initial condition of 0, 1, and it's the function is its own derivative. But let's talk about how to solve this one analytically, and then maybe we'll look at this one. Okay. So let's see. I want to change colors here. To solve the first order differential equations we're going to see in here, we're going to use a technique called separation of variables. Again, this, unless you've already gone on to lesson 2, the second part of the lesson, you haven't seen this yet. That's okay. Separation of variables is really cool. And we'll be practicing it more on Tuesday, but I figured let's go ahead and take a look at it. We'll do this one, and maybe we'll go back and look at this one again here as well. So here's how you do it. So we know the differential equation is y prime equals 1. Well, instead of writing it that way, I'm going to write it as dy dx equals 1. And now you're going to see why it's called separation of variables. We're going to get everything in terms of x on one side and everything in terms of y on the other. But with separation of variables, and this part's very important, you can only move stuff from side to side using multiplication or division. You cannot use addition or subtraction. Okay, so when you guys get to that part of the online lesson, I want you to keep that in mind. When you're looking at examples of the lesson, notice how every single one is done with multiplication or division. There's no addition or subtraction to separate the variables. And here's what I mean by that. I'm going to do this one in 2 steps, but in the future, I'll probably just do it all in one. Basically, what's happening is, whoa, I don't know what just happened there. Oh boy, come on, what's going on? Having a technology issue here for a second, guys. Let me see. Great. Let's try. Maybe this will work better. Oh, shoot. Okay. Whatever was happening seems to be okay. Okay. So here's what basically was happening. I'm going to multiply both sides by dx. You know, that cancels out the dx is over here. I get dy equals y dx. And I want to put the y over with the dy. So I'm going to divide both sides by. Now, this is why it's called separation of variables. We just separated the y's and the x's. Okay. What we do at this point is we integrate on both sides. Now, this goes back to Calc 1 and what we were doing earlier this semester. You're basically taking an antiderivative on each side, one in terms of y, one in terms of x. Antiderivative over here is ln of y. You can make it absolute value of y, but once we go to solve, the absolute value goes away, so you don't have to worry about it. Over here, antiderivative of dx is x. And now both of these are general antiderivatives. So at some point, we need a plus c. We could add plus c's on both sides, but there's no point in doing that because if we had plus c's on both sides, and we wouldn't want to use the same c because they'd be different. So we might like, you know, if we did something like this, plus c1 plus c2, well, we're just going to subtract c2 over and absorb that into a different constant. So we don't need to put c's on both sides. So we're only going to put c's on the right-hand side. Do not worry about putting c's on the left-hand side. Sorry. There we go. So we do that. Okay. And all those are the solutions to each of these differential equations. Then what we want to do is solve this for y, however we need to solve it. Well, to undo a law, we have to make both sides exponents of e. Okay, so let's come up here. E to the ln of y is equal to 1. And this is why we didn't need absolute value. And that is equal to e to the x plus c. Well, that doesn't quite look like the general solution we saw before because it had a multiplicative constant. Here's how that works. E to the x, we know that, plus c. Well, this can be rewritten as e to the x times e to the c. E to the c is itself a constant. So we absorb that into another, it's called absorbing a constant. So we absorb that into a new constant to make it a little bit more simplified, call it a, and we get e to the x times a, or the way we were used to seeing it, a e to the x. All right. Now what that looks like, the absorbing constant, it's going to depend on the differential equation. We're only going to look at 2 examples today, but you're going to see more in the online lesson for Tuesday. And we're going to get a lot of practice with this on Tuesday, okay, the separation of variance. I just want to show it to you now because we just had a short time left, and I think it's a nice warm-up for when you get into that next lesson. And now you involve your initial condition and you get the unique solution. Questions about that before we go on? Okay. Now, and actually, before we do, where did our slope field plotter up? Yeah. Let's do this. Sorry, that's a little bit of a mess there. Let's do this before. Let's see what our slope field looks like. We should always take a look. And we got to get rid of those solutions there. Okay, so pretty interesting looking. Now we're only going from 0 to 1. Let's put in a few more line segments. And we only care about, we're sorry, 0 to 2. So let's -1, 2, 3. And our initial condition was 0, 1, which is about right here. And if we follow our slope field, see how it's concave up? It kind of curves upwards, right? We're going to expect this to be an underestimate of the actual value. Now, let's find the actual value. So we're going to do the separation of variables like we just did, except for this this function, this differential equation. So dy dx equals x squared over y. Our initial condition was that it goes through 0, 1. Okay, that's going to be what we use to find the constant. First thing we do is separate the variables. So basically, we're going to put the y over here, the dx over here, right? That'll get our variables separated. So we have y dy equals x squared dx. Once we have them separated, we integrate both sides. Pretty easy antiderivatives on this one. Y squared over 2 equals x cubed over 3 plus c. We need c at some point. Where do we find c is completely up to us. We could find c right now if we want to. So let's do that in this. Let's do this. Let's make it a kind of a separate. Find c. So to find c, I don't like. I don't know why I wrote it there, but let's do this. All right. So next thing we're going to do is we're going to find c. Nothing crazy going on here, guys. Put 0 and 1 in. Now, what I mean by finding c now, we know we need to solve for y. So you could solve for y first, then find c, or you can find c and then solve for y. It actually does not matter. As long as you do everything correctly, it'll come out fine. Sometimes it's easier to find the constant first. Sometimes it's easier to find it later. For example, the one we did before, this one, it's easier to absorb this constant first, then input the initial condition, then as opposed to doing it here. But you could do it here. It's still going to come out correct. But for this one, I'm just going to do it now. And I don't know that it's any easier or harder. I just wanted you to see that you guys have that option. So we're putting in 1 for y. So 1 squared over 2 equals 0 cubed over 3 plus c. Well, that leads us to c equals 1/2. So we found our c. So here's where we're at. Y squared over 2 equals x cubed over 3 plus 1/2. If you want, you can find a common denominator, add those together. Nothing wrong with that. All right. Next thing we do is we solve for y. It's true, you might run into differential equations that cannot be solved for y. But whenever we can, we do. And most of the ones we'll do in this class, if not all, can be solved for the output variable. So next thing we do is solve for y. All right, well, we have y squared over 2 equals x cubed over 3 plus 1/2. Well, clearly we need to multiply both sides by 2 to get rid of that 2. So we're going to end up with y squared equals 2x cubed over 3. It's distributing plus 1. And lastly, y equals square root of 2x cubed over 3 plus 1. Now, I want to show you something interesting, and it's something we do not want to forget. So I'm bringing here's our slope field. Sorry, everything's so messy. Here's our slope field. Notice that there's slope field above the x-axis as well as below. Well, This solution only gives positive y values. So depending on what our initial condition is, we may need to consider the positive or negative. Now, because we're starting above the x-axis, we only need to consider the positive case. But if our starting point was 0, -1, we would need to consider the negative case. Okay? We don't. We know ours is positive. Now, here's why we're doing this. We estimated that y of 2 was about 2.33256. Well, now we're going to find out exactly what it is. So, y of 2 equals 2 times 2 cubed over 3 plus 1, square root of all that. All right. Well, shoot. There we go. All right, now I lost my calculator. All right. Okay. So let's put this into the calculator. We'll just put it all at once. Square root of 2 times 2 cubed divided by 3 plus 1. And there's our actual. Oops, sorry. 2 points. So it came out to be about 2.516611478. So, like we predicted, based off the slope field, we did have an underestimate of the actual. But that's what Euler's method is doing. It's giving us an approximation of what the solution function would give us. Now, just like with numerical integration is only necessary when we can't find an anti-prime. Euler's method is only necessary when we can't find the unique solution curve to a differential equation. The thing is, in life, that happens pretty often. So we do need to be familiar with these numerical methods. Now, we're doing them on ones that we can calculate because we want to be able to check the answers and make sense out of them. So in practice, we would never do this one. We probably wouldn't do this one with Euler's method because it's very easy to do analytically. But we're doing it here because I want you to see what it is that Euler's method actually approximates. And what it's approximating is the solution functions, the unique solutions functions, y value for a given input. Okay. I know I just threw a lot at you guys, and we're actually already a minute over time. But I want to see question. I'm fine with hanging out a little bit afterwards if you guys have any questions about this. Now, again, I did skip ahead with the separation of variables. You have not seen that yet, but now you have. So when you see it in the online lesson, it's going to look already familiar and you'll get some more practice with it. And what we'll do on Tuesday, we'll do a little bit more separation of variables, and then we're just going to dive into some of the applications and make this stuff a little bit more interesting. But questions at this point? So the three things that I want you to feel at least comfortable with as you get to the homework. We did verifying solutions of a differential equation. We looked at slope fields and the representation of general solution, a unique solution. So basically what a differential equation gives us, what it is, how do we solve it, and then Euler's method. Separation of variables, again, really isn't one of the topics for today. It's actually more of a topic for Tuesday, but I don't think there's anything wrong with getting ahead so we can actually make sense of what Euler's method is actually giving us. All right. Any questions at this point? Anything that we talked about today